Okay, so the first question was saying that state the laws of solid friction. This one I've seen it. You said that um,
The image is kind of
okay. So you can read for me what you wrote.
uh, frictional force opposes the attempted or relative motion between surfaces in contact.
That is correct.
The second law of friction is independent of the area of contact of surfaces, but depends on the nature of surfaces in contact.
Very good.
Then the frictional force is directly proportional to the normal reaction between surfaces and is independent of their relative velocity.
And is independent of their relative velocities. Okay, that is very good. That is fine. Then part B, a car of mass 1,000 kilograms moving along a straight road with a speed of 72 kilometers per hour is brought. So in this question, we have the initial velocity, which is 72 kilometers per hour. You change this one to meters per second. So it's the same as 72 kilometers out of 1 hour, which is the same as 72 kilometers, multiply that by 1,000, get 72,000 meters and 3,600 seconds. And this, I think, will give us 20 meters per second. Is that fine? You should be having a calculator with you. Then it is brought to rest. That means that the final velocity is 0 meters per second. By a steady application of the brakes in a distance of, so we have our distance as 50 meters. Find the coefficient of kinetic friction between the tires and the road for max. So how do you find the coefficient of friction? The coefficient of friction is got from simply F is equal to mu R, where our mu is the coefficient of friction, and then the F is the friction, and then R is the normal reaction. Okay. Now, according to the question, the car was moving on a straight road. Assume that this is our road here, and then this is our car. That is our car. They're saying that it is moving with a speed of 70 kilometers per hour and brought to rest by a steady application of the brakes in a distance of 50 meters. Find the coefficient of sliding friction. Let me allow this one, okay? So, how do you find the coefficient of sliding friction? If the resultant force, if the body is going in this direction, hey, what is happening? If the body was going in that direction, it means this way we have the driving force, and then backward we have the frictional force. So from the second law of motion, from Newton's second law, we have that our F is equal to ma. Okay, our force is equal to ma. And this F represents the resultant force. It represents the resultant force, which means therefore that our resultant force will be the same as the capital D minus the frictional force, the resistance to motion. This one will give us ma. So we are using this equation here simply because we are able to get the acceleration from the given information. And if the brakes are applied here, it means that the engine is no longer exerting a force. So the driving force is 0. So if this is our equation star, we can first get our acceleration from S is equal to ut plus a half at squared. But when we look at this one here, we don't have the time. But again, we can use this equation here, the third equation of motion. V squared is equal to u squared plus 2as. We have the final velocity, we have the initial velocity, we have the distance covered. So when you substitute into this, we shall have 0 is equal to, the U is 20, we change it to meters per second, then plus 2 times A times the 50. What acceleration do you get? Yes, what acceleration are you getting? Christian, Martina, Rodney, you're all welcome.
-4 meters per second squared.
-4 meters per second squared. So our acceleration is equal to -4 meters per second squared. That is very good. That is correct. So we have the acceleration, we have the mass, the driving force is 0, and then we're supposed to find the frictional force. So from our equation star, we've said that our D minus the F is equal to MA. The driving force is 0 because the brakes are being applied. If the brakes are being applied, then the engine is exerting no force. The engine of the car. So our driving force is 0 minus the F. This is equal to our mass, which is 1,000, times our acceleration, which is -4. So this will give us our frictional force as equal to dash in newtons. And from the frictional force being equal to mu r, our force will be equal to mu times the normal reaction. The normal reaction will be the weight of the body. So our weight, which is equal to mg, and then the normal reaction. I'm using the capital R, but the idea is supposed to be from here. That is R1, and then from there, which is R2. Because the normal reaction acts when we have contact. So when you add up this R1 and then R2, we shall get our normal reaction, capital R. So this is the same as mg. What friction have we got here in the question? It will be is that fine? Are you there?
Yes.
So 4,000 is equal to mu times 1,000 times 9.81. And therefore our mu will be equal to that answer there, 4,000 divided by
0.41.
0.41. Okay. 0.41, correct. 0.41. No units. No units. Okay, did anyone get this right?
I did.
I did.
You did get the answer. Yes, I didn't see your work. I didn't see your work. If you got it, well and good. Let me see what this one got.
Work.
They messed up.
Oh. Okay, I think for you skipped this.
Yeah.
You skipped that. Okay, let me see another one. Yeah, you skipped this question. Okay, no problem. So in case you didn't get it, then you can do the corrections. You can do the corrections. So what was challenging here? I can hear from you. What was challenging, Andre?
I don't know which law to use.
Yes, Rodine. Rodine has gone. Okay. I think the network is disturbing him. So let's go to the next number. The next number, it is saying that a bullet of mass is 0.012 kilograms and horizontal speed of 70 meters per second strikes a block of wood of mass 0.4 kilograms and instantly comes to rest with respect to the block. The block is suspended from the ceiling by means of a thin string. Calculate the height to which the block rises. And then Roman 2, estimate the amount of heat produced in the block. Okay. So what do we do here? Can I remove this working? Can I rub off?
Yeah.
Okay. So number two, I mean part C, we have that information there. This is about the ballistic pendulum. It's about the ballistic pendulum. Remember that in the ballistic pendulum, the aim of that experiment there for the ballistic pendulum is determining the velocity of the bullet. So it looks like this. Assuming that this is our point of suspension, we're having a block and a bullet. This is our block. So the bullet comes and then strikes the block. So they're saying that once the bullet enters the block, it comes to rest instantaneously. Yeah, instantly. It comes to rest instantly. The rest of the block. So so as a result, the two are going to be suspended. I mean, they're going to be inclined to the vertical like this. Like this, with the block inside there. With the block, I mean with the bullet inside there. The bullet inside there. So this is the point of reference where we're going to be measuring the height from. So this will be our height here. Two people waiting in the Rodney. I think the network is disturbing him. Okay.
Yeah, he's been texting me to this internet.
So this is our height h. So the question says that a bullet of mass this, so in case I have my bullet of mass of the bullet as 1, then U1, this is U2, mass M2, and then the two after collision will be having a total mass which is capital M and a total velocity which is capital V. I'm just using that because the two will be moving as a single body. So calculate the height to which the block rises. Now, when we're doing this, when we're looking at this, during the lesson, we said that we are going to be using two principles. One is the principle of conservation of mechanical energy, and then two is the principle of conservation of momentum. Rodney, Christian, are you there?
Yeah, I'm here, sir. I'm here.
Okay, that's great. Great to hear from you. So we're using the conservation of momentum and then the conservation of mechanical energy. Whenever you see any question,
Not clearly.
when you're dealing with questions concerning the ballistic pendulum, any question, always look at these two principles here. What does the principle of conservation of momentum say? How do we state it? Anyone to remind us? Yes. Principle of conservation of momentum. Okay, it says that when two bodies collide, the total momentum is always a constant, provided no external forces act on the system. That is how it states. Or someone can simply say that when two MO bodies collide, total momentum before collision is equal to momentum after collision, provided no external forces act on the system. That is our principle of conservation of momentum. Then how about the conservation of mechanical energy? For the conservation of mechanical energy, remember mechanical energy is all about potential energy and then the kinetic energy. That's what it's all about. So mechanical energy is the sum of these two here. So the principle of conservation of mechanical energy simply says that when a body is moving, maybe it is moving up or down in a constant force field, that is under gravitation, constant force field, the sum of the mechanical energy at any one point is always a constant. That is what it says, that when you add mechanical energy, kinetic energy plus potential energy at any one point in a gravitational field, you'll always get the same value, you always get a constant. So if this is point A, and then this is point B, at point A shall only be applying the principle of conservation of momentum, and our mass of the bullet in the question is 0.012 times its velocity, which is 70. The mass of the block is 0.4. Its velocity is 0 because it is originally at rest. Total mass, because the two will be moving together as a single body, we have 0.012 plus 0.4, then times the V. What is the V that we get here? What V did you get?
Um, 2.04.
2.04, correct?
I got 2.0.
Meters per second, correct? So this is the velocity of the body just after impact at this point here. At this point, just after impact. Now, as the body is moving from A to B, let me write this other side. From A to B, we are using conservation of momentum. And what does it say? It simply says that total energy at this point, mechanical energy at this point is equal to total energy at this point here. Or simply you can say that loss in kinetic energy is equal to gain in potential energy. Loss in potential energy is equal to gain in loss in kinetic energy is equal to gain in potential energy. Gain in potential energy. Why am I saying this? Because at this point here, the body is having maximum kinetic energy, but as it is moving upwards, the altitude is increasing, the height is increasing, so the potential energy is increasing. So all the kinetic energy at this point is going to be converted into potential energy when the body finally comes to rest at point B, and that will give us the height h. So from a half mv squared equals to mgh. Of course, at this point here, you can even see that the m cancels out, and our height h will simply be equal to a half divided by g times the v squared. So what does this give us? It will give us 0.5 times the velocity. We've got 2.04, but you square this, then everything divided by 9.81. The answer that you get will be the height of the body. Or you can simply say that from v squared is equal to 2gh. So you have your 2.04, but you square this is equal to the square root of 2 times 9.81 times the h. This equation here is simply coming from this. If you make v subject of the formula, that is how it comes. So when you simplify this, you'll find that your h is equal to, what do you get? in this case?
0.212.
0.212.
0.212 meters. And that is our answer. That is our answer. Did anyone get this?
Yeah.
Yes, I got it.
Okay, that is great. But it would be better if I saw your work and I marked it. Even if you tell me that you got it right, I have no authority to say that you didn't get it.
But teacher, I sent you the work.
Yeah, send me the work. I'm going to check again and see. You sent it via WhatsApp.
Yes, I sent it last week.
Oh, I'm going to check and see. Okay, that's good. That's good. Then I hope I can remove this. I hope that you're even following what you wrote in your book or your paper. In case you did something wrong, you correct it. You try to correct what you messed up. I hope that Christian, we are together. In case of anything, please ask. Okay. So the next question is saying that estimate the amount of heat produced in the collision. Estimate the amount of heat produced in the collision. How did you do this?
I didn't do it.
Okay. Anyone else? Andrew, what did you do?
Same answer.
You didn't do it as well.
Yeah,
Okay.
it's tricky.
Yes, what you're going to do here is simply the change in the kinetic energy of the bullet. In other words, if the bullet comes like this, remember this is an inelastic collision. An inelastic collision. So if it is not a perfectly elastic collision, remember in perfectly elastic collision, we say that kinetic energy is conserved and momentum is also conserved, meaning that the two remain the same. Momentum before is equal to momentum after. Kinetic energy before is equal to kinetic energy after. But if it is not a perfectly elastic collision, then the change in the kinetic energy is always converted into the other forms of energy. So for this case, we assume that that change in energy will be converted into the heat energy. Now, using that idea there, this is our bullet. This is before collision, and then this is after collision. So let's get the total kinetic energy before collision. Kinetic energy is equal to a half m1 u1 squared plus a half m2 u2 squared. But this one was equal to 0 because the body was at rest. So for the bullet, we shall have, this is the same as a half times the mass of the bullet 0.012 times its velocity, which is 70 squared. What do we get here? Then after collision, we shall have that our kinetic energy is going to be equal to a half m1 plus m2 into v squared. So this is the same as a half into 0.012 plus 0.4.
29.4.
29.4.
Yeah.
Then times 2.04 squared. This is after collision. What do we get here?
Um, 0.857.
0.857 joules. Do we get that, members? The rest? Okay, we get the same answer. So the loss in kinetic energy is equal to the kinetic energy before minus the kinetic energy after collision. So this is the same as 29.4 joules minus 0.857. So whatever you get will be the loss in kinetic energy, and that will be the same as the heat produced in the block.
28.543.
28.543 joules. Okay. Okay, that is fine. That is fine. I hope I can now remove it. It is now clear.
Yeah.
Okay.
Yeah.
Then last but not least, define the following terms: Roman 1 momentum, Roman 2 impulse. So Martina, what did you write here?
Momentum is the product.
Yes, Martina? Okay, Andre, what did you write?
The product of mass and velocity.
Correct, simply that. It is mass times velocity, product of mass and velocity of a body. Okay, and then impulse.
Amount of force applied to a body for a period of time in order to cause a change in momentum.
In order to cause the change in momentum. So you can either define this like you've said, or you can simply define it as the product of force and time for which the force acts. And in that definition there, I'm interested in how we describe this time here. We define momentum as the product of the force and the time for which the force acts on the body, the time for which the force acts on the body, or you can simply define it as impulse being equal to the change in the momentum of the body. Change in the momentum of the body. In other words, impulse is the same as the final momentum minus the initial momentum. Where does it come from? It is simply coming from F is equal to MA, which is the same as M into V minus U out of T. And when you cross multiply, you find that our Ft is the same as M into V minus U. And this is the same as the impulse. So impulse is defined as the product of the force and the time for which the force acts on the body. Or simply the change in the momentum of the body. Okay. 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 So the next question is saying that state the work energy theorem. Two identical balls A and B of mass 1.5 kilograms are moving with velocities this and 5 meters respectively. It is found out that after collision, the total kinetic energy is lost by the balls is 37.5 joules. Find the velocities with which the balls move after collision. Did anyone do this?
Yeah.
Okay, how did you do it? Let me check. I guess this is the one.
Why is your screen kind of blurry?
It is blurred simply because I have magnified your image. That's why it is not clear on that side. It is not clear on that side.
Very clear here.
Okay. Work energy theorem. How did you state it?
States that the network done by the force of one object is equal to a change in its kinetic energy.
It's equal to the change in the kinetic energy. That is correct. That is correct. In other words, if a body starts from here and covers a distance u or distance s, this is our distance s, and it is being acted upon by a constant force F from point A to point B, from work being defined as the product of the force and the distance moved in the direction of the force. This is equal to Fs. I can put that on my equation 1. And then also, if I'm to change this force, if I'm to change this distance S in terms of the U and the V and the A, I'll simply have this, that if the body is starting with the velocity U and is ending with the velocity V in a time t, I can simply say that from acceleration being equal to V minus U out of t, and our force F is equal to MA, I can simply say that my force F is equal to the mass times the V minus the U out of the T. But from the third equation of motion, V squared is equal to U squared plus 2AS. I'm trying to rush here simply because of time. So first of all, you have work done from this equation here. And I want to substitute for the force F in this equation, and then for the acceleration A, and I see what I get. Okay, and I see what I get. So from the third equation of motion, I'm having that V squared is equal to U squared plus 2AS. It implies that my S will be equal to, I'm making S subject of the formula, S will be equal to V squared minus U squared out of 2A, out of 2A. So if this is my equation Roman 1, and so if I try to put this Roman 1 into equation 1, I'll simply say that my work done is equal to the same as Fs, which is the same as where there is S, where there is F, I can put it there, M into V minus U. No, let me put it there, the MA. And then where there is S, I'll put it there, V squared minus U squared out of 2A. So from this equation here, we can see that the A cancels out, okay? Implying that this is the same as when I open the brackets here, I'll end up with a half M V squared minus a half M U squared. This is my work, the expression for the work. So our work therefore will be simply the same as the change in the kinetic energy. And that is what Rodney has mentioned to us, that the work energy theorem states that when a force acts on the body, the work done is equal to the change in the kinetic energy of that body. That is what we call the work energy theorem. It states that when a force acts on a body, the work done is equal to the change in the kinetic energy of the body. That is the work energy theorem, this statement here. I can give you some time to note this down, to note that down. So meanwhile, we can be looking at number 2, but let me first pause here.